Hello everyone, this is Mr. Santos once again with lecture 5, Introduction to Procedures. Okay, here we're going to give a brief introductions on procedures. We're going to talk about why we need them, how are they useful, how do they work. We're going to talk about the stack. You cannot talk about procedures without having some discussion involving the stack. We're going to talk about how to write safe procedures by using the push and pop instructions, which push data into the stack and retrieve data from the stack. We're going to talk about what not to do when writing procedures, and then after that we're going to finish quickly with a demonstration with Atmel Studio using the simulator to show you some of these concepts and you can actually see them in action. Okay, so let's just go ahead and get right to it. So what is a procedure? If you're familiar with programming languages, you have heard of them under a variety of names. You know, in assembly they're called procedures, sometimes they're called routines. In the C programming language, for example, they're called functions. In object-oriented language, they're called methods. But basically, a procedure is a reusable piece of software, okay, within your code that you can reuse over and over again to complete some kind of task or to process data in some way or to compute some value. Okay, so basically a procedure is a reusable unit of software. So you have your procedure, okay, and this procedure usually consumes something. It has some information that it needs, and how many pieces of information that it needs, that's up to you. You know, we could just use mathematical notation. You know, in mathematics you have a function, the concept of a function, right? And you always write it in a mathematical way that the result y will be some operation indicated by this function when we provided all the parameters that it needs. All right, so you pass it the function these arguments, and then after that it produces some result. A procedure does the same thing. It is a representation of this, but in software, right? So you write a program that constitutes a procedure, and then you give it pieces of information, and then that procedure may or may not produce something once the procedure has completed. Okay, so that is the essence of what a procedure is, and it's very closely related to the concept of a mathematical function, but it's not quite the same because in mathematics we always take numbers. The objects are always numbers, and what it returns is always a number, right? In procedures we may perform a task. We not necessarily act on numbers. We may act on abstract objects. You know, we may act on strings. We may act on I/O ports, things like that. We may compute some value. We may not need to compute some value. We may transform a bunch of data in memory in some way. You know, it's more than just a mathematical function. But the general essence of what a procedure does is this, you know, with this being optional. Now, the motivation of what you need procedures, usually when you are a novice programmer, no offense, you write your code, you may have some piece of code that is really long, right? You just write whatever comes to your mind. You don't think about design. You don't think about restructuring and organizing your program in a way that, you know, where you practice useful, you know, good software design skills, right? But then as you write code and as you get experience, you will notice that there are certain parts of code that, you know, for example, you have something here that looks really familiar and almost the same thing that you're doing here. And then you find yourself that you're actually writing the same piece of code, but maybe there might be a few things that change. You know, there might be that one variable where you do everything the same, but then that one parameter is the only thing that changes. You know, here is 2, here x is 7, here x is 5, but the rest of the thing that you do in this particular chunk of code is always the same, right? You're repeating yourself over and over again, and then these, you know, let's say this is like 20 lines of code, and this is 20 lines of code, and this is 20 lines of code, where you program just added at least 60 lines of code, and most of it is the same thing, right? Why not write a procedure? You could instead write a procedure, right, that takes x as a parameter, and then it maybe produces some result. right? Now, instead, you can eliminate this whole thing. You write a procedure that is separate. A procedure is separate from the program. I mean, you could put it in the same code listing file in the same .asm file, but it's separate from the main. The main code, the first part of the program that execute, we usually call that main. Okay, and instead you replace all of this by simply calling a procedure, right? And you can just say call procedure with whatever the parameter is here, and then you change this and replace it with simply a call to the procedure with now the parameter 7, because that's the only piece of within the whole code that needs to change. And then you call the procedure again with a value of 5. Now when you program execute from top to bottom and it finds the call instruction, it just jumps to the procedure with the corresponding value, it does its thing, and then it comes back where it started, and then it finishes, and then it calls the procedure, it does its thing, and then it comes back, and then it continues. So this will be gone, and now your code decreases by at least 40 lines, because you just have one call instruction, and then you have your only 20 lines of code here. Okay, so code reusability is the key here. Alright, when you have a program, procedures help you to solve a problem by way of the divide and conquer approach. Okay, so you got one big program here, and instead what you could do with procedures is that you could divide the problem into smaller problems, and with each of these subproblem or subtask, each of these could be a procedure. So here you have your main code, and somewhere in here you have a few procedures. So then you have this procedure, and then that procedure in turn can call other procedures. That's perfectly legal. Okay, you could have procedures. If procedure 1 calls procedure 2 and procedure 3, they're all procedures. And then procedure 2 again, which might that might give us recursion. Let's just call it procedure 4. Might call still procedure 2 and maybe another newer procedure, procedure 5. Right? So you could divide and conquer the problem that you want to do. Okay, so that's the essence of procedures, and you definitely want to design programs, and you want to take advantage of procedures if you can figure out a way to write them. Okay, now let's get specific. In Atmel AVR, a procedure always starts with a label that ends with a column. Right? This is the same label that you use to when you want to jump to somewhere within your code. For example, we talked about infinite loops in the program. So, you have your code in here, and usually in embedded systems, you have a label, and then you just jump back to itself. Right? We have an infinite loop that never ends. Right? This here is a label. Well, procedure also starts with a label, except with the difference that now you have to enclose the code that is part of the procedure between a label and a return statement. Okay, so here is where you put your code for the procedure, and it's always sandwiched, if you will, between a label and a return, and the name that you put here is the name of the procedure. Okay, so if you have a procedure called add two numbers, for example, let's say, again, procedures always take some data, so you need to designate some registers that you will use as data that will be consumed by the procedure. Alright, so in the previous diagram you saw that conceptually you have some variables, some information, and you have your function, and then you have y. Okay, in programming we do the same thing, but we don't have variables. Instead we use registers. So you can use some register here, and then another register here. Alright, and then you put the result in yet another register. That's all you have to do, and here's your procedure. Okay, so if you wanted to make a procedure called add two numbers, right, just for demonstration purposes, okay, you could call the procedure add numbers, right, and then after that all you would do, and suppose that the procedure expects the number to be in R16 and R17, and it puts the result in R18. Okay, so then all you would do is add R16 and 17, then move the result into R18 from R16, then return. Then somewhere in your main code, you say, I want to add two numbers. So, you could say LDI R16 2 and LDI R17 3, and then call add numbers, and then after this instruction executes, then R18 should have the value of 5, right? So you always put your code between the label and the return. All right, and that's it. That's pretty much just the essence of a procedure. Okay, now suppose I wanna let's talk about the stack before we move on. Okay, now we want to write safe procedures. Okay, now the stack is an area of memory where you can store information temporarily and return it back. Okay, when you use procedures, for example, let's get back to our example. Suppose I want to write a procedure that adds the contents of R16 and R17, and it returns the result in R16 still. So notice that we have, as inputs, we provide the value here and here, and then we put the result in R16. So after this procedure completes, it's going to overwrite whatever you had initially, and that's perfectly fine, right? One problem that I find students have is that they don't know how to make efficient use of registers. The Atmel has 32 registers named from R0 to R31. Okay, and what they will do is that they'll start with R0, and then for the next instruction they'll use R1. Then for the next instruction or the next thing they need to do, maybe they'll use R2 and R3. Then they have a delay routine, but in the delay routine they use R5 and 6. And then they have another delay routine that does something else, or a display routine. Then they use R8, 9, and 10, for example. Well, you only have 32 registers. What are you going to do after you run out of registers? You can safely actually write a program that only uses at most 1, maybe even 2 and 3 registers. And that's it, over and over again without any danger. How do you do that? You use the stack, okay, by using the push and pop instructions. Okay, so the stack is an area of memory. That's not very straight. Come on, you can do better than that. Let's do that. Let's do that. Okay, so this is the stack somewhere in memory. This is SRAM of the ABR. Somewhere at the top of the memory, okay, we set up the stack pointer. This is a register composed of 2 bytes, a high byte and a low byte. Actually, I think it's called SPL, SPH. So let's call it the way they're actually called on the ABR, right? And these are each 8 bits, but together they form a 16-bit address that points to the location in memory where you're going to store data. Alright, so what happens is that when you use push, for example, if I use the push instruction R16, whatever's in R16 is going to be placed here. So for example, if R16 has the number 3, which would be stored as 03 in hex, then 03 will be placed in there, and then the stack pointer would decrement by 1 word or byte, and then it will be ready if you call pushed again. So for example, I have R17, and R17 has the value 7 for whatever reason. So then after you execute this instruction, then the stack pointer is going to put 7, and then it's going to decrement by 1 byte, and then it's going to wait for you to put something else. Notice the addresses, let's just say down here is 0, so address value is the increment until the maximum address. Let's just give it a symbolic name and call it RAM end. The end, this is the last byte of the entire SRAM, right? Then you do something, and then right before you finish, you need to restore R16 and R17 to what they were before you did everything. Let's say somewhere in here you needed to use R16 and R17 again, right? So you're going to lose these values because you're reusing them. You're overriding them with something else. Well, you could safely do that. Reuse R16, R17, and then whenever you're done doing whatever it is that you're going to do, you restore them using the pop instruction. But we need to notice that I use 2 pushes here. So I'm going to need 2 pushes to restore 16 and 17, but I have to do it in the reverse order because my pointer here, this is for R16, this was for R17, and my pointer is now sitting in here. When I use pop, the pointer is going to go backwards, back up, right, in reverse order. So therefore I have to restore this guy first. So I pop R17, then 7 is going to be restored back into R17, then the pointer is going to move here, then I pop R16, then the pointer is going to increment and then restore R16 to its original value. But notice that they're in reverse order. This is very important. Push 16, push 17, pop 17, pop 16. So if this were a procedure such as add numbers that we saw in the previous example, okay, this is how you would write it. And then of course we would have the return, right? Pushing and popping always occurs at the beginning of the procedure, and popping always occurs in reverse at the end, immediately preceding the return statement, most of the time. Okay, there may be some cases where here you may push again some other register, and then somewhere in here you should pop again that same register. Okay, so this causes this procedure to not disturb at least 16 and 17. So then in your code, this is your main code, you know, you use R16 and R17, and then somewhere in here you call add numbers, right? You execute, it goes in here, it does this, and then it returns back. Well, at this point in this line, R16 and R17 are still going to contain the original data before you call. So you could call another procedure, say, you know, call some other procedure and continue, right? So if you use push and pop within each procedure to restore, to preserve the state of input values only, then you can continue to use the same registers over and over again throughout your program. For example, you could have a delay here. Suppose you have a delay. You know, let's kind of revisit that example. Suppose you have a delay routine. I don't know how that routine works, right? But that routine works by you decrementing R16. So this delay will form a loop. It will look at the value of R16, and it will continue decrementing the value in here until it reaches 0. And then when it reaches 0, it returns, right? So in your program code, in main, you would write your code, and then let's say you needed a 5 millisecond delay. Let's suppose this is each loop is in milliseconds. So then you would do something like LDI R16 2 milliseconds. Let's say you wanted to delay 2 milliseconds. Then you call delay. Let's suppose right after that maybe you execute 2 lines of code and you need to call delay again with the same number of milliseconds, right? Would this work? The answer is no, because without pushing and pop, right, before the delay gets executed, R16 equals 2. But remember that the delay is going to decrement R16 until it reaches 0. When R16 equals 0, then the procedure is going to return. So that means that when we get to this line, at this point, R16 equals 0. So therefore, we have a problem here. This is a bug. right? What's going to happen here is that when we call delay again, R16 will be decremented, and then it'll wrap around from 0 to 255, and then it'll give you 255 millisecond delay, which is not what we want. This can be fixed in two ways. Number one, we just reset R16 to 2. And that actually probably should be the way to handle this. But another way is to preserve the input value that the procedure uses. Since this procedure uses R16, maybe the safe thing to do is that immediately when we start, we push R16 to preserve its initial value. Then when we are done, somewhere here before we return, and we exit the loop, we have to exit the loop, then we pop R16. Now we do the first delay, we set it to 2, we call delay decrements R16 until it reaches 0, but then when it returns, it restores it. So at this point, even though here it was 0, R16 gets restored to its original value, which here it was 2. Right? Now when I call delay again, here R16 already has the initial value of 2, and I'm good to go. Right? Not only that, I can use, well, actually, let me retract that statement. I'm not going to say what I was going to say. Okay, but basically, this is how you will write safe, reusable procedures, pushes and pops for whatever registers you use. Now, I need to caution you about something here. When you write a procedure, again, let's go back to that diagram. Let's say you have a procedure that takes a value in R16, or it needs a value in R16, it needs a value in R17, and it needs a value in R18 before it gets called. And then that procedure produces a value in R16, and it produces a value in R20. It doesn't matter why. Okay, that's how you wrote the procedure. Okay, when you write a procedure, you only want to preserve at the beginning of the procedure. You always want to preserve only those variables that serve as inputs but not outputs. Okay, if you need to write something in the output, then when you pop the value, you will actually restore the original value that was there, and you're not going to be able to reuse it, which is silly. So therefore, since I use 16 here also to return some information, I should not push R16. I should only push R17 and R18. Okay, so in this procedure, you would only push R17, push R18, do your thing, and then pop in reverse order R18, pop R17, and then return. Right? Because the reason is you're going to use R16 and R17 to return something back. If I push R16 here and I pop it down here, then I'm going to erase whatever it is I produce for R16 here, because you're now restoring R16 to whatever it was when the procedure started, which is silly. So to write safe procedures, I want to repeat again, reusable procedures, make sure you push and pop any input values that you're using that are not output values, that you need to return information back after the procedure completes. Alright, let's show some of the stuff actually in code. So once again, I need to remind my viewers, if you're a general viewer, that we do things in a specific way, that we have to do it in our labs. So usually we create, when we start a project, we start with an empty solution instead of just going straight to a project, because we provide our students with some project templates. So let's just say call this procedure tutorial underscore solution. Hit OK. Then we right click here and we're going to add a new project, which will be the simulator. We'll use the simulator template, call it procedure tutorial, but this time underscore simulator, and hit OK. There is the initial code that we have in our project template, and let's just try some things. And of course, for you, please always make sure that you fill in the comment header. This is always important. But the template that we provide you, procedures should always go after the infinite loop, because we want to prevent the code from just continuing to run and run into the procedures. And I will show you that. Well, let's just write a procedure that let's call a procedure that adds our two numbers like we wanted it to do. Okay, so let's just say add numbers and then return. And we're going to start basic. So again, all we want to do is add R16, R17, and move the result in R18 from R16, because for whatever reason that's the way that we want to design it. Okay, also when you write procedures, you should always add some description of what that procedure does, you know. So adds two numbers and returns the result in R18. So usually you want to specify what your input arguments are. What does the procedure expects from you before it can do its job? So you could say R16, R17 should contain numbers to add, and then output args. You can have R18 contains the sum, and you should do this for every procedure you write. Okay, don't just write a procedure and just leave it like that, like people are supposed to figure out what it's supposed to do. Okay, now setting up the stack. What did I say? Whenever you write procedures, you must never forget, always set up the stack. Alright, and please make sure that you add code in the right place. We always add code after the start. Don't add it right here where we say place data. That's for data. Okay, code goes here. Let's set up the stack. To set up the stack, we load the stack pointer. Stack pointer is 16 bits and it's divided into two registers, a low pointer and a high pointer. So first we need the stack pointer of the end. So we show you here, let's see what page was it. I said that the end of memory for the AVR device is defined by some constant called RAM end. This constant actually happens to be defined inside of the include file. So you don't need to know what the value is, other than the constant exists by name. So we could just say load into R16 the low byte of the value represented by RAM end, and load into R17 the high byte of the value represented by RAM end. Okay, low and high, these are macro functions that extract the low byte and the high byte respectively. Okay, you need to know how it works, so just know that these macros already do the job for you. And then lastly, we need to write the stack pointer itself. So since the stack pointer registers are I/O registers, we need to use the output instruction. So out onto the low stack byte, the value in R16, and output into the high stack byte, the value in R17. Next, we want to add the two numbers. So we load R16 with 2, load R17 with 3. We prepare the input parameters, input arguments. Then we call add numbers here. Okay, now let's go ahead and build this. So right click, build, and then let's go ahead and start the debugger. Okay, you should have the I/O window. Actually, we don't need the I/O window this time, but we'll leave it open. Registers, processor status, reminder again, all this stuff is accessible by these icons over here. Okay, we also want to look at memory. So in memory, I already have a place. You can actually type an address here. Notice that when we start, here on the processor status, you can see with the stack pointer. So it shows you what address in memory the stack is pointing to presently, which is 8FF. So I went ahead here and typed 8FF. First of all, you need to select these. With the memory viewer, you can see various memories. So program flash is where the code is stored, but the static memory is the internal RAM. So you need to select IRAM. Okay, and usually you will have to start the first instruction. So suppose I hit F10 to step once, and then we'll get the data to appear. Then here you could type 08FF. Select 08FF, press enter, and maybe scroll here a few lines of code so that we could see. So this is the end of memory, right? Now we're going to load value into 16 and 17. So I do F10 once and F10 again. Notice that 16 has FF and 17 has 8. And that was originally already the initial value because the simulator already does this for you. But you should always get in the habit of doing this yourself manually so that you know that the stack is set exactly where you want it. Okay? Excuse me. Now we're going to load SPL and SPH, but it already has the same value, so we're not going to see much of a difference. But essentially, excuse me, that's how you would do it. Now we're going to invoke our instruction. So we do load 16.2, load 17 with 3. Now we're going to step into, not step over, step into. And I want you to watch the following. Notice that the stack pointer is pointing at the end of the stack. Then we hit F11. And notice that before we do anything, the stack pointer has decremented by 2 bytes. That's because when you call a procedure, a call instruction does 2 things. It saves the return address so that it knows how to. You see this return statement here? That means we want to come back here and continue the program. Well, how does the procedure know where to return back to? Well, to do that, it writes the address of where to come back to. So this instruction here is address A. Okay, or sorry, this instruction here is address A. We are now address A. I'm getting confused here. The address is 9. And in fact, remember in lecture 1 I showed you that when you create a project in Atmel Studio, let me go ahead and open my documents, go to Atmel Studio, go to my tutorial, simulator, debug, and the list file. You remember this? List file is the expanded version of the code of your .asm code that also shows the contents of the include file. In fact, if I do, well, I don't know if RAM is, let me see if RAM end is RAM end. It is defined there. It is already equated there. That's why we don't have to know the value. It's in the include file. But anyways, if we scroll to the bottom, here's our code. It shows you the disassembly of the code and the address in memory of each instruction. So here, the call instruction is located at address 7. After the call is done, you want to return to the next instruction, which is on address 9. Notice that here, when we pushed and decremented the stack by 2 bytes, it has the address 0, 9. That's what we're going to return to. We're presently, I was getting confused because I was saying A because the first address of the procedure add numbers is at address A. That's what the program counter is showing you, address A. We go ahead and add these 2 numbers. Add, so 16 has the answer of 5, and then we're going to move it to 18. So 18 now has the answer. And then we return, and notice that right now the stack pointer is at FD, so it's going to pull back those 2 bytes, and then it comes back to where it's supposed to be. Notice that the stack pointer is back to the beginning, which was FF. The stack pointer does not declare what's in there. It leaves it there. So the next time you write something into the stack pointer, it'll just overwrite these values. That's okay. For the same reason that the move instruction doesn't actually move, it just copies. That's all. Now, that's without using push and pop. If I were to use push and pop, let me go ahead and stop this. To write this safely, again, only write push and pop for input values but not output values. What is the one output value for this procedure? Only R18. So I can safely say push R16, push R17, and then we pop in reverse. Pop R17, pop R16, Control S. Just for fun, I can actually now call at numbers again because upon return it's going to have the same value. Now I may want to save my result from my first add. Maybe I might move R19, the value that was in R18, returned by my first call. Control S, debug. Once again, F10. We set up the stack, so I'm going to hit F10 4 times. 1, 2, 3, 4. Then I set my parameters that will be needed by my add numbers procedure. I set those parameters. Then I go ahead and step into. Notice my stack pointer is as FD, so it got decremented by 2 because the return address has to be saved. But then I push again. So I push R16. Notice that R16 is now on my stack, and the stack pointer decremented by 1. And then I push R17. Notice that R17 is now in the stack. Notice that my stack pointer decremented by 1 again. Then I do the job of what I need to do inside the procedure. Then I restore R17 to what it was and R16 to what it was. Okay, notice that R16 and 17 have the original values, but I don't change R18 because I need to leave it there because that's where my answer is. Then I return. My stack pointer goes back to the beginning. Okay, and notice that at this point, now I'm back in main context, and notice that R16 and 17 still have my original values, so I don't have to set them again. I move the answer from 18 to 19, and now 19 has a copy of the answer, and I can safely call add numbers again with the same parameters, and we finish in forever. But notice that now R18 and 19 have the same answer. It still worked safely. Notice that at the end of the program, my stack pointer is back where it started. This is another thing you want to identify. When students write many procedures, they forget to put the stack or pop the stack, or maybe do it in the wrong order, or usually they'll forget to pop. If at the end of the program you're not back where the stack pointer is supposed to be, then you know your stack pointer was corrupted. Something went wrong. You didn't have the same number of pushes and pops. Okay, always remember that. Same number of pushes and pops, and they have to always be in reverse order. Okay, one last thing of what not to do. Sometimes I see some students that what they will do is that they will write a program, then they will call a procedure, and then let's suppose you have some other label here. Let's just call this label 2. And we do something. Let's just do nothing. Put a few no ops in there. And then they'll try to do something like this. Okay, and then right here they'll do an R jump to label 2. Okay, this is a huge mistake. You don't want to. You never ever jump out of a procedure onto somewhere away from that procedure. The boundaries of your procedure are always between the label and the return statement. When you get here, you're jumping away from that boundary back into main. Not only that, you jumped into main, you did not call that, and then you have a return statement. Every return statement must be complemented by a call instruction. You call to a procedure. You don't jump to a procedure. You never jump to a procedure. You only call. Now, you can jump, so this should never happen. You never jump out of a procedure. If you want to jump from a procedure to another procedure, then write another procedure that does something and then it returns. Okay, so if you need to do that, then you call another procedure, but you never jump out of a procedure. Okay, you can have labels within the procedure. So I can have something like label 2, and then you do stuff, and then for some reason, maybe this is a loop, and then you are jump to label 2. This is legal because you're staying within the procedure and you're jumping back to the same within the same procedure. But you never jump out of here anywhere or anywhere else. You can call a procedure, can call another procedure, and then when it returns, it'll come back and it'll continue, and then when it reaches the other return, it'll go back to main. But you never jump out of a procedure. Everything should be contained within the procedure. If you jump, all jumps should occur within the procedure, etc., etc. Okay, that's pretty much it. I hope that the video was useful, and you should now be ready, be able to learn how to write, how to use a stack, number one, and number two, how to write proper procedures, how to be able to safely reuse the same registers over and over again by using pushes and pops. Okay, I want to reiterate the fact that whenever you're writing procedures, okay, that you only save, you push only input variables but never output input registers, but never output registers, because then you're overwriting your output. Okay, all the time. And then once you have that, you could simply, in your code, you could always copy your functions and paste them onto the next project and reuse them again, because they're safely written and you don't have to worry about one procedure overwriting the registers of your program, which creates problems. Okay, or you don't have to use all 32 registers because you didn't know how to, keep them straight in your head when you were writing your program. Okay, it is a good way again to divide and conquer the problem, and to write reusable code, and to write clean software programs. All right, that's pretty much it. Thank you for your time, and see you next time.